Okay, hello. I'm sorry for yesterday's afternoon. I didn't prepare my. I forgot to send my teaching material to my nine. Usually, I prepared my teaching material and transfer my teaching material into PDF file, and then I have to send it to my night, and I use my iPad to download it, to open it, and use how to say that good note to conduct my lecture. But Wednesday night, I forget to do these things. So next week, I will prepare a drink for you. If you need more, please tell me from the night group. Okay. So today, I wanted to introduce elastic to data from published from NTU, Professor Liu. This is about nanosheet. Nanosheet is interesting structure for the future. So several weeks ago, I showed you how to fabricate the nanosheet by Lego, right? So you might know how to fabricate a nanosheet, but very important, how to fabricate nanosheet in the university, and then by just discussed silicon nanosheet is useless. So for university, we have to discuss germanium, 2D materials, and SI semiconductor. Okay, so because this we can call this material future work. But about germanium, several years ago, we still have a several group dedicated in germanium fabrication, especially Professor Zhu Liu. So they proposed several interesting idea to fabricate the germanium nanosheet. So next, I will review the two of their IDM papers. Okay, so the first paper, they demonstrate a four-stack and a germanium tin. Okay, last time I told you that we needed to have a very high etching selectivity. Okay, we have to find materials with very high etching selectivity, but how to form the nanosheet is an important the issue and the technique. So usually if we for the industry, they deposit the silicon germanium and the silicon, and they use etchant for to etch out silicon germanium, or in the future for PMOSFET, they will use the etchant to remove silicon and keep etch out the silicon and keep the silicon germanium for heterogeneous integration. So this is our dream. Our dream, we want to have high mobility N-channel. High mobility N-channel may be the material for high mobility N-channel may be silicon. Germanium is good, but the germanium there are a lot of problems like interface, like band gap, like dopant activation efficiency. So maybe silicon will be good enough. However, we have tried a lot of approach to improve germanium, include CO2 laser, include N2H4, hydrogen treatment for the interfacial layer, and then currently we have pretty good germanium MOSFET, but as compared with silicon, our germanium MOS is not good enough. So we still have a team dedicated themselves in germanium MOS fabrication. So for this is for MOS, and for PMOS, this is for PMOS. PMOS may be silicon germanium, maybe germanium. Yeah, germanium PMOS is a mature technique, so it's very easy to achieve a high on-off ratio. So it's no problem to use the germanium to replace the silicon germanium and silicon. But the problem is, the AP and high temperature reliability. So we don't have a good high temperature reliability such as MBTI, and then the AP, the dislocation, the germanium quality for high yield is still still a big issue there for the future. So we still have some problem about germanium, and then but I think at least we need a silicon germanium, and the the concentration of germanium should be I think should be larger than 20%. If we can have higher than 20%, it will be good. Lower than 20% is good for epitaxy growth, because the dislocation density is pretty low if the germanium concentration is less than 20%. So for FinFET, we have silicon, and we have silicon germanium PFET, we have silicon NFET. For nanosheet, from my point of view, we still need silicon for NFET and the silicon germanium for PFET, especially the orientation concern. This is 110. 110 could benefit whole mobility. So if we change the architecture of CMOS from a vertical direction to horizontal direction, right? So it become 110, and very small ratio of the total width is 110. So nanosheet is not good for PMOSFET. I told you several weeks ago. So we need a silicon germanium. Silicon germanium could boost the mobility of hole, so we can balance the performance between silicon and with silicon and silicon germanium. Okay. Another approach is a germanium team. Germanium team is a very interesting material. Could bring with to come up. We can have a higher hole mobility from a germanium team, and then germanium team. The silicon and the germanium are in direct band gap. So silicon and germanium is very typical for optical application. So usually, we don't like to study silicon and germanium for optical application. But for TIM, if we have a higher germanium, a higher tin concentration, and the indirect band gap can become direct band gap. So Professor Liu investigate in a germanium, the for higher hole mobility. So by using this approach, we can have a higher hole mobility PFAT. Actually, the interfacial layer is pretty bad for germanium from my point of view, because we have a paper related to germanium published at the TD 3 years ago. So I don't think it's suitable to use a germanium for PMOSFET at current stage. This is because we have to solve the issue of interfacial layer and the germanium quality. But to demo this idea for IDM publication is no problem, because for IDM and the VSI, for IDM and the VSI conferences, you have to demonstrate the new idea, and and a lot of people will review your paper, and then they will evaluate this idea is good or not. So several years ago, 5 years ago, they published several papers about stack germanium, and then the next paper, let's say they boost the uncurrent, and then they use a low channel doping and a high substrate doping, and the low channel doping can suppress the scattering effect, which can increase mobility, and then high substrate doping can suppress the ice, the sheet resistance of the substrate and the contact resistance. So to suppress these two parameters, you can boost your current. Okay, and the next paper is about work function. Work function is another issue, especially for CFAT. And then in 2021, Professor Xiu Liu published this paper to discuss about the ALD tungsten nitride carbide work function metal. So I think for this class, I want to discuss these two papers. Okay, for the first paper, they proposed a highly selective isotropic dry etching. So isotropic dry etching is pretty important for nanosheet. This is because in the future, in the past, we have to use an isotropic etching to form a vertical etching profile sharply. But for nanosheet, we still need an isotropic etching to form the nanosheet active region sharply, and then we need isotropic dry etching to etch out the the material between channel A and B, C, and between channel A and channel B, and channel B and channel C, So the layer between channel A and channel B and channel C should be etched out. So we need isotropic dry etching process, and then it should be very high selective. This is because we have to keep a germanium, and then the layer, underneath the germanium or between the germanium should provide a high selectivity as compared to germanium. It's reasonable, no problem. It's reasonable, okay, no problem. But the problem is during the epitaxial growth process, we have to escape dislocation during the epitaxial growth process. So two things: selectivity, S is means selectivity. The second one is dislocation density. So epitaxial growth for superlattice, you have to consider the critical thickness and also the dislocation density caused by the lattice mismatch. So critical thickness is very important. Usually, if the dislocation density is pretty low, the other problem is the selectivity is also low, because I think like a silicon and the germanium layer etching selectivity is pretty large, but the dislocation between silicon and germanium is pretty large. So if we want to solve the problem, so you have to use a silicon germanium, and the germanium concentration should be low. If the germanium concentration is low, the etching selectivity will be low. So this is a big problem. So usually, if we have to take care both etching selectivity and dislocation, you may consider trade-off situation. So after etching, the width will become smaller, and we have a round corner. And it becomes smaller. So this is the trade-off between the etching selectivity and the density, dislocation density. Okay, so let's read this paper. The effective effect of doping 11 on the channel and the etching characteristic stacked germanium PMOSFET are demonstrated recently to achieve high uncurrent GM, but with uncurrent high, also the occurrence is also high, because their high uncurrent is due to the small hole effective mass under large compressive strain, and also the band gap becomes smaller, so the occurrence increased a lot. So it's very difficult, from my point of view, it's very difficult to to boost the uncurrent ratio to uncurrent ratio larger than 5 order. Usually 4 order is regular, so it's very difficult to increase the uncurrent ratio from 4 order to 5 order from my point of view, because we did a lot of a transistor, and then we don't see any any improve for the arm ratio. So this is a very the big problem. Okay, and the etching rate of silicon germanium and germanium in weight H2O2 etchant weight is decreased by boron doping. It means as we try to dope the material of silicon, germanium, and germanium with boron, the etching rate could be suppressed. Okay, so but the doped channel suffer mobility degradation by impurity scattering. So this is a very important point of view. Usually in the past, we use light doping to adjust the source drain. Okay. We call it VTH adjustment. Very light doping, about 1E13, okay, centimeter square, minus a square. So very light doping to adjust the VTH, to adjust the VTH. So usually we have to use very higher dope to suppress the saturation effect. Unfortunately, higher the dosage will cause the lower mobility. So after that, we use a packet or halo or anti-puncture. This is anti-puncture. The purple is anti-puncture to suppress the saturation effect. So I mean, we have keep the channel in low dopant concentration. This is because the dope channel suffer mobility degradation due to the impurity scattering. Okay, and the next is about dry etching and wet etching. The boron doped the germanium channel and undoped germanium sacrificial layer. SL means a sacrificial layer, means we have to remove it later. I used it to okay, here I used the previous to obtain the necessary etching selectivity for germanium channel released by H2O2 etching. So actually they have another paper. They use boron. They use the boron doped germanium, and they use H2O2 channel to remove germanium with with germanium, and then how to to keep their germanium. They use boron dope, which but the trade-off is I think etching selectivity and mobility. So dry etching is very important. So radical bath the highly selective isotropic. Okay, so how to achieve the isotropic dry etching process? You have to turn off the back bias of the etching chamber, or you can use remote plasma to generate the plasma, and then introduce the plasma from the remote plasma chamber to etching chamber, and then you can enjoy the isotropic dry etching. So usually for dry etching chamber, we use an F3 to clean the chamber. So usually we have a remote plasma chamber for NF3, and then after NF3 the plasma generated, we have to the flow introduce the M3 plasma into the chamber. So this high slide etching is demonstrated in this study with very high selective between P plus germanium, and on top germanium. And I think this time they use a different idea. In the past, in the previous paper, they used germanium top, and germanium on top. It's very interesting, but you have to consider about the sojourn for the university that we don't have a selective AP process flow. We don't have a selective AP process flow. So this is the top view. Of the MOSFET, and then let's cut this line, and the cross-section view is this is the germanium, germanium, So the area for channel is here. So for channel, we have to release the channel and etch out the germanium and keep germanium, right? Okay, but here for the social area, we will keep this. So we cannot use a sojourn implantation for the sojourn. What happened? What is the reason we cannot use ion implantation to top the sojourn? I think that actually you can use you can use sojourn implantation, but you have to use the photoresist to cover the channel area because it's I think the height is pretty I think the height is pretty large. It's pretty large, so maybe 200 nanometer, and then we need a high energy ion implantation to I think to implant the dosage to implant I think some ions into the substrate, and then the distribution, the amorphous layer, I think the amorphous layer would be large enough. Okay, so if the channel suffer such high energy ion implantation, the channel will become amorphous, and the channel will be totally damaged due to the ion implantation. So this is a very big problem, and also you may say that professor, it's pretty easy to use the photoresist to cover the channel material. However, we still have some problem. This is the channel area, and this is the social area, and usually this is gate. And it's impossible to cover gate area only. So we need a larger photoresist to cover here, and then I think that so we have some area. This area will be undoped, so the ice will be high. So Professor Liu used this approach. Actually, they use a very smart approach to suppress. Actually, they still have some. They still have some on top region, but they use P plus Germanium and the germanium to suppress the social and the resistance. Okay, but actually it's not a good idea for the industry. The industry use selective AP, but for the university, such a problem is pretty big. So this is a reason we cannot produce very high performance MOSFET as compared with the industry, because we cannot shorten the distance between gate and the contact hole. This is because of the misalignment from the Lysakov tool. Okay, this is the first problem. The second problem is we don't have selective AP growth. I think in TSI or in ONCU. Okay, so let's discuss their previous paper. So they use a very interesting idea. They take a big, I think, very the hold, and then use a PT to form the PT germanium tin and PT germanium to suppress the uncle, and then this is also the problem. Okay, because we still have to suffer high resistance the area. Okay, and then this is their layer. They they use the silicon germanium cap, and then they have a high the strength germanium tin channel, and the concentration is about 12%. 12% is a very very high. Okay, 12% is a very high concentration. Okay, and then here let's set the bond top the germanium channel, and the on top germanium the sacrificial layer are used previous to attain the necessary etching selectivity for germanium channel released by H2O2. So they use this material. They use such kind of stack because of the way etching the restriction limitation. So because we just I think at the time we just have the from our knowledge we know H2O2 is a very good weight etching for germanium, and then if we can have something which can if we can have something can resist in H2O2 etching, they will be good. So they use this approach. They use this way for their first paper, and then the dopant the channel suffer mobility degradation by impurity scattering. So the next year they change. So they change their structure. So to further improve the mobility for the germanium channel, the on top germanium channel is designed with a boron top. Okay, so at the first they have a boron top the germanium, so they keep the germanium, and they use a boron and then now they use a germanium tin on top and the boron top germanium to reduce the suction region at the same time. So this idea is a little smart. I think how to say that it's a smarter than lead. than their previous idea. But you know that although this idea is not good enough, but you know, 5 years ago, 6 years ago is a new idea. So from my point of view, you all have to be very, brave to to challenge yourself, to choose a tough topic to overcome. That I think that you just have 2 or 3 years for your master degree, your master degree, and then you can choose a very simple a topic for your master degree program. But you are young. I suggest you to change yourself and try to fabricate a cutting edge transistor to prove you're somebody. This is pretty important. So from their new idea, they don't need to dig a deep hole for their social area. So in Chinese, I said in the past, this is just like to go to a dentist, 根管治疗. I have no idea how to how to speak it in English, but I think it's very close to 根管治疗. And then for their new idea, because they have I think adopted a germanium sacrificial layer, so they can keep here their social area could be provide their social area, the resistance of their social area is low, so no problem. They don't need to act a decode. And then how to use the high side etching process to remove the germanium. So I think they finish this transistor at TSRI. So I think that's no problem to it's no problem to finish this structure at the TSRI. Is not the tip code and pretty easy. And another the important point from this paper, usually they have to they use SOI. This is 8-inch SOI wafer. It's pretty expensive. Per wafer is I think it's $20 and 22,000 $20. Okay, and then because of the outside layer, so it's very easy to form the mesa structure, and then the acceleration could be achieved by using mesa architecture. Pretty easy, but the problem is the epitaxy growth, and especially the dislocation between the germanium and the silicon, or germanium and the silicon, due to the lattice mismatch. So they have the thick buffer layer. This is a thick buffer layer, and then they have to use a high temperature anneal in the vacuum chamber. That the chamber for epitaxy growth is a vacuum chamber. I think it is very close to 10 to -5 torr. So sometimes they will use they will introduce some hydrogen to improve the dislocation area dislocation density, to suppress the dislocation density in the vacuum chamber. Actually, a long time ago, I saw the TM picture. I saw the TM picture for this. I think you know the differences between with and without 800 degrees Celsius near process. Okay, the dislocation density could be suppressed a lot after 800 degrees Celsius in a near process. Okay, and then actually we will have a buffer, a parasitic germanium channel here, and then from the structure, because in TSI we just have a get first. We just have get first a process flow. So we will have a parasitic germanium channel, which will cause some problem now. So this is a problem. So they use a very smart idea to remove the parasitic germanium channel, and then actually they do some comparison. They said their IV curve, their current are not from the parasitic germanium channel. I think this is a very important claims for their structure, because some people, some some attack from from the web, from the internet, said that if we have such a parasitic germanium channel, the uncurrent should be from here. Okay, so this is the epi layer designed and device, the optimization. So this is a very beautiful germanium, very beautiful germanium super lattice epi, and then this is on top. So if you check, if we don't have the high temperature near in vacuum chamber, you will see a lot of black, okay, how to say that, black a spot here, something like that, like use black. You have to see a lot of black, nice here. So let's say the interface is very clean, but actually a TM just provide a local, the local analysis. So I think for the university, for professors, usually we said okay, the interface layer is very clean, right? Pretty clean. And then the dislocation could be suppressed a lot, and it's possible to use this layer for mass production. Actually, no. I don't think the industry will use this to use such kind of wafer for their for mass production. This is because the standard for mass production is very high. So you cannot, I think you cannot use such material just because of one TM image. You need to use a lot of data to evaluate such kind of process. Okay, so they have the B-top sacrificial layer, pretty thick. So actually the I think the height is pretty thick. The 60, 44, 44. No, 54, 54, 60, and then I think it's over. I think it's very close to 200 nanometer. So this is a very, I think, a large height. Okay, so the process, the etching process, would be very dangerous. From my point of view, it would be very dangerous. And then the thickness for the germanium is 18 nanometer only. So it's hard, it's difficult to release the. It's not it's difficult. Actually, we wanted to the release to etch out the germanium silicon, but the thickness is 20 nanometer only. Okay, not easy. So usually after the joint process to define active region, you will have a lot of polymer here, polymer here. Okay, so if you don't without polymer removal, it's impossible to etch out the germanium, the sacrificial layer. It's almost impossible. So we have tested several times by using LE, and sometimes the etching selectivity is over 200. Sometimes no etching. The etching selectivity is very close to 1. No, actually 0. Almost no etching. So we have discussed such embarrassing situation with the engineer. The engineer said that actually LE at the interlock they use high temperature maybe 300 degrees Celsius to 400 degrees Celsius to remove the polymer. But actually it's not easy. So usually we use a test wafer to check the etching selectivity, which is good. The etching selectivity is larger than 200. So we are so happy, and then we load in the I think the product a coupon wafer for ourselves, and after 10 minutes, oh my God, nothing happened. Actually, we have no idea what happened. Why nothing happened? Okay, so the polymer is I think is a tricky layer. During the isotropic etching, you have to remove the polymer first. Okay, so this is their epi-layer design and device optimization. So for this week, this is their germanium. So for Raman, for PLO, they have a narrower and a stronger PLO peak, and then this is SM. This is the SRT. So they have very good, that is the distribution is tight and small. It means the distribution, I think the quality of the germanium or the epi layer is good. If I think if the width is large, it means the crystallization is not good enough. So from this SRD, that means they have very good germanium. Okay, and for their SIMS profile, you can see that. Okay, this is a boron. So, okay, sorry. So their boron Okay. Okay. Leopold is in the Germanian, and in the German team they don't have Born, so which are pretty interesting and good for their the epi layer. Okay, it's time for yesterday's class. Sorry again, and next week, next Tuesday, Thursday, I will keep delivering my teaching material. Okay, thank you.